In the previous video, I made a mistake, that is numbering the carbon atoms in propene. The numbering should start on the double bonded carbon, so that carbon 1 is here, 2 and 3. Now hyperconjugation can result in such structures. The CH bond shifting in this direction, the Y bond is shifting over carbon, carbon gains a lone pair of electron and a negative charge, and H remains as H positive in close contact with the pi electron system, and the net result is that C2 to C3 bond acquires double bond character. Now in the most stable canonical structure, C3 to C2 bond is a single bond, whereas in hyperconjugation canonical structures, the C2 to C3 bond is a double bond. So the bond length of C2 to C3 bond should be in between a carbon-carbon single bond and a carbon-carbon double bond in the real structure or the resonance hybrids. Now the approximate structure of the resonance hybrid is shown here, where the C1 to C2 and C2 to C3 bond has pi bond character, partial pi bonds. Now the C2 to C3 bond in actual propene molecule is found to be experimentally having a bond length of 1.488 angstrom units, and the C1 to C2 bond length in actual propene is found to be experimentally equal to 1.353 angstrom units. The usual carbon-carbon single bond length in any molecule is nearly 1.54 angstrom units. You compare this 1.54 with 1.488. So the actual bond length value in propene for C2 to C3 bond is slightly less than a normal single bond, showing that there is hyperconjugation operating. Again, the C1 to C2 bond length is 1.353 angstrom units found experimentally in propene, and the usual C double bond C structure is having a bond length of 1.33 angstrom units, and this value is slightly higher than this value. This shows that the double bond character is slightly decreased because of the contribution of such canonical structures where the C2 to C1 bond is a single bond, so that the bond length between C1 and C2 will be in between a double bond and a single bond, and again it is more close to a double bond because of the lesser contribution of character of such a canonical structures due to the charge separation. Now let us compare the stabilities of two isomeric molecules called 1-butene and 2-butene. Now 1-butene is this one, where the double bond starts on carbon 1 and the CH bonds on carbon 3 are alternate to this double bonds. So hyperconjugation can operate, and only two such structures are possible. CH bond shifting in this direction and the pi bond here shifting over this carbon, so that the electron pair in the pi bond is entirely moving into the orbital of carbon, giving it a negative charge, and there is a lone pair here, and H as H positive is in close contact with the pi electron system. Now only two such canonical structures are possible for 1-butene, so that its free energy decrease is less, and so it is less stable than 2-butene, because in 2-butene there are 6 CH bonds conjugated to or alternate to the double bond. So 6 hyperconjugation canonical structures are possible for 2-butene, so its free energy will be lower than that of 1-butene. And again we have seen earlier that greater the number of canonical structures, higher is the extent of electron pair movement, and higher is the stability, lower the free energy, etc. Now in thermodynamics there is an equation F equals H minus Ts, where F is the free energy. F is also denoted by another letter G, Gibbs free energy, G, both are same. H is the enthalpy, T is the absolute temperature, and S is the entropy. Entropy is a measure of the number of possible ways in which a system may be distinguished. You take the example of ethane molecule. You have seen two prominent conformers for ethane, that is eclipsed and staggered conformations. Now when eclipsed conformation is rotated around the carbon-carbon single bond to 60 degrees, we get the staggered conformation. Suppose we are rotating the molecule about the carbon-carbon single bond from the eclipsed conformation through 1 degree, we get another conformer which is a distinguishable form. You rotate it to 2 degree, then we get another conformer which is again a distinguishable form. So you rotate the carbon-carbon single bond to any degree, we get conformers which are all distinguishable forms, so that a large number of distinguishable forms are possible for a ethane molecule by rotation about carbon-carbon single bond, so that its entropy is appreciably high due to the presence of a large number of distinguishable forms. Now in the most stable canonical structure for 1-butene and 2-butene, we have carbon-carbon single bonds, here 2 single bonds, here 2 single bonds, and rotation about these single bonds can produce a large number of conformers, so that the most stable canonical structure has a larger number of distinguishable forms, hence a larger entropy for both 1-butene and 2-butene. But when we come to the resonance hybrids, the carbon-carbon bonds acquire double bond character. There is only one single bond in the case of 1-butene, and there is no single bond in the approximate resonance hybrid of 2-butene. All bonds have partial double bond character. Here 2 bonds have partial double bond character, and free rotation about a double bond, whether it is full or partial, is not possible. So the number of conformers is restricted. In the case of 1-butene, there is a single bond, but in the case of 2-butene, there is no single bond, true single bond. So the bond between all the carbon atoms in 2-butene are partial double bonds, and so that free rotation is not possible. So the number of distinguishable arrangements in the resonance hybrid is lower in both cases, so that S is lower for both the resonance hybrid of 1-butene and the resonance hybrid of 2-butene. So F is lower because the electron pairs can move over the chain of atoms through hyperconjugation, and S is lower because number of distinguishable arrangements are low, and if F and S are lower, then H should be lower. So the enthalpies of the approximate resonance hybrid of 1-butene and approximate resonance hybrid of 2-butene should be lower. Then the stabilities of these 2 butenes, that is 1-butene and butene may be compared by measuring experimentally the quantity called heat of hydrogenation. Hydrogenation reaction is the addition of hydrogen to a double bond or a triple bond. So here one butene possesses a double bond and two butene possesses a double bond. When hydrogen adds to these molecules, we get the common product, that is butane. Now during addition, the pi bond breaks, creating two valencies over the carbon atoms. The HH bond breaks, creating H with a valency, another H with a valency. The valency over this H will be uniting with the valency created here, producing a CH sigma bond. Here also a CH sigma bond is formed, and the CH sigma bond is a stronger bond. So during its formation, a very large amount of energy is released. So two CH sigma bonds are formed, liberating a large amount of energy, so that the enthalpy of the product butane will be lower than that of one butene or two butene. So butane is having a lower enthalpy due to the formation of strong CH sigma bond. Stronger the bond, higher is the energy liberated. Bond formation is exothermic, whereas bond breakage is endothermic, we know. So during formation of strong CH bond, sigma bonds, a large amount of energy is liberated, and so butane has a lower enthalpy than one butene or two butene. Now heat of hydrogenation is the difference in enthalpies of the reduction product and the reactant molecule, reactant alkane. So actually here the enthalpy of the product minus enthalpy of the reactants. So heat of hydrogenation here will be having a negative value, but when we take the magnitudes of heat of hydrogenation, the magnitude will be higher for one butene because it has a higher enthalpy, because it is unstable, compared to two butene, which is more stable, again due to the presence of a large number of hyperconjugation canonical structures. Its enthalpy will be lower because of its free energy is lower and entropy is lower. So when we calculate the heat of hydrogenation values for one butene and two butene, it is found that the magnitude of heat of hydrogenation is higher for one butene and magnitude of heat of hydrogenation for two butene, particularly the trans isomer, which is shown here. The trans 2-butene is shown here. The methyl groups are far apart, hydrogens are far apart, and this is a stable structure. And the trans 2-butene has a heat of hydrogenation value whose magnitude is lower, 27.6. So lower the heat of hydrogenation value, the higher is the stability of the alkane. Now we take the example of nitromethane, a specific example where methyl group is connected to a nitro group. A nitro group has a resonance where the lone pair of oxygen atom here moves into the direction in between nitrogen and oxygen. We start the arrow from the negative charge. It is enough to start the arrow from the negative charge to indicate that the lone pair is moving in between N and O simultaneously. To maintain the valency of nitrogen, the pi bond here is moving over oxygen atom, creating a lone pair here and a negative charge, so we get this form. Now in the resonance hybrids, there is double bond character for NO bond here and NO bond here, as shown by this structure, so that we write the structure of the resonance hybrid as this one, where dotted lines start from oxygen atom through nitrogen atom, passes to the other oxygen atom, and the charge is shared by the two oxygen atoms, that is delta negative here and delta negative here, and the interaction between, that is repulsion between these two charges, are minimized due to the angle 120 degree here. So this angle is 120 degree, so there is minimum repulsion. And again, nitro group shows a strong electron withdrawing character due to positive nitrogen and double bonded oxygen. Positive nitrogen is as electronegative as oxygen, and double bonded oxygen is as electronegative as fluorine. So we say it can show a strong electron withdrawing character indicated by minus inductive effect, which we will see later. So the strong minus effect of nitro group combined with the hyperconjugation makes the hydrogen acidic, in the sense H positive is made free during hyperconjugation, so that this H positive can move on to the negative oxygen here or the negative oxygen here, so that the nitrogen molecule is acidic, and hence we write the structure CS2 double bond N positive O bond H O negative, which is called the acid form. Acid form indicates acid form. Now here, during hyperconjugation, what happens is that H positive is moving over to an oxygen atom. So it is no more hyperconjugation, but it is another particular phenomenon called tautomerism. And during tautomerism, one atom changes its position from a given atom to another atom. During resonance, there is no change in position of any atoms, whether it is hyperconjugation or isomeric effect or resonance. There is no positional change of atoms. Relative positions of atoms are maintained in resonance, but here there is change in position of atoms, and the phenomenon is called tautomerism. The acid form is acidic, and this particular structural unit NOH bond O is similar to C double bond OH, which is the structure of a carboxylic acid, and a carboxylic acid is acidic in organic chemistry. So acid form is acidic, and then the acid form can ionize, the OH bond can ionize as O negative and H positive. Now the angle between the two inner bonds is 120 degree, so that these negative charges are far apart, so that they cannot repel. And again, this anion, which is also called the conjugate base, is stabilized by resonance, the O negative shifting to a position in between N positive and O negative, means the lone pair over O negative is a shifting in between N positive and O negative, establishing a bond. And to maintain the valency of nitrogen, the pi bond here is shifting over this carbon, so that we get CS2 negative. Of course, a lone pair is there, which is not shown in this structure, and double bond O. Now this canonical structure for the acid form can be repeated by shifting of this electron pair over or shifting this electron pair in between N and O, and a simultaneous shift of this electron pair over carbon atom. So an equivalent structure or a similar structure like this one is possible. So this electron pair movement over the entire atoms makes the free energy of the system less, so that the anionic structure is also stabilized by resonance. This favors the acidity of this form, which is called the acid form. So the anion is more stabilized by resonance, and hence it's a driving force for ionization of these OH bonds into O negative and H positive. So much about hyperconjugation, and if you have got any doubts, please inform me. Let us pass on to another effect called the inductive effect. You consider a carbon chain, a chain of carbon atoms connected to an electronegative atom, that is chlorine. Now the electronegativity of chlorine is 3.2 and that of carbon is 2.5. Due to this electronegativity difference, the electron pair between carbon and chlorine will be slightly shifted towards chlorine as shown in this figure. The electron pair between carbon and chlorine is slightly shifted towards chlorine. Now this shifting will create a slight negative charge denoted by delta negative on chlorine and a consequent positive charge over carbon, alpha carbon, denoted by delta positive. Now delta positive carbon is slightly more electronegative than a neutral carbon, so that the electron pair between alpha and beta carbon will be slightly shifted towards alpha carbon. Now this shift will not be of the same magnitude as the shift between carbon and chlorine, because here there are two carbon atoms of comparable electronegativity, means the electronegativity of a neutral carbon is 2.5 and that of delta positive carbon is slightly greater, and so the shift of electron pair between alpha and beta carbon is not so much as the shift between carbon and chlorine, so that there is only a very slight shift of this pair of electrons as shown by this figure, and this carbon gets a slightly lower positive charge than delta positive. If delta positive is 1/2, then delta positive equals delta into delta positive, that is 1/2 into another fraction, say 1/4, that is 1/8. So if delta positive is 1/2, then delta positive will be 1/8. That means delta positive is higher than delta positive. So delta positive is lower than delta positive, and this delta positive, which is lower than delta positive over beta carbon, will very weakly pull the electron pair between beta and gamma carbon, so that the shift of electron pair between alpha and beta carbon towards beta carbon will be still lower than that between alpha and beta carbon, so that gamma carbon gets delta positive, which is of lower magnitude than delta positive. So delta multiplied to another delta multiplied to another delta will give a still smaller fraction. But when we add all these delta values, positive values, when we add delta positive and delta positive and delta positive, we get delta negative. So as the chain length increases, the magnitude of positive charge carried by the carbon atom decreases to such a lower value that we can neglect the positive charge over the other carbon connected to gamma carbon. So beyond gamma carbon, the effect of this electron withdrawing character or electron shift may be neglected. Now chlorine, by using its higher electronegativity, we can say actually withdraws electron density from the carbon chain. Now this electron withdrawing character of chlorine from a carbon chain is called negative inductive effect. So electron density is withdrawn from the carbon chain by electronegative chlorine, and the phenomenon is called negative inductive or minus I effect. Now what is the impact of chlorine when there is a pi bond present in between beta and gamma carbons. So there is a pi bond between beta and gamma carbon. Now we know that pi electrons are overlapping away from the internuclear region, so that there is lesser hold of the atoms which form the pi bond over the pi electron pair, so that the shift of this pi electron by the inductive mechanism is less. So pi electrons are less shifted by inductive mechanism when the position is between beta and gamma carbon. But when the pi bond is between alpha and beta carbon, if the attached atom is chlorine, then resonance can occur, mesomeric effect can occur like this, giving negative charge over the beta carbon and positive charge over the chlorine atom. And if the pi bond is between alpha carbon and the attached atom, as in the case of C double bond O, then resonance can occur like this, that is shift of pi electron pair over oxygen atom, giving a positive charge to the alpha carbon and negative charge to oxygen. So the impact of pi electrons over the impact of inductive effects over pi electrons vary according to the position of the pi electron pair. If the pi electron pair is far away, then it has got little impact, and if the pi electron pair is between alpha and beta positions, then the mechanism operating is that of resonance. Now examples of groups showing minus I effect. When the atom directly connected to carbon chain is more electronegative than carbon, always the effect is minus I effect. So nitrogen atom with an electronegativity of 3 when connected to this carbon chain shows minus effect. Oxygen atom with electronegativity 3.5 when connected to this carbon chain shows minus effect. All halogens which are more electronegative than carbon when connected to carbon chain shows minus effect. Then groups like nitro, COH, CHO, C double bond O, C triple bond N, NS3 positive, all contain atoms or groups with a more electronegative atom connected to the carbon chain show minus I effect. Thank you.